Here are some examples on your assignment 3.5. So again, like for most questions, there's a B, C, and D. I'll do one or two. If you want me to do more, just let me know. Okay, so question one, it just wants us to write the Ka expression for each acid ionizing in an aqueous solution. Include values for Ka from the data booklet. And so for the first, I'm going to do C here, so it's a little more complicated. Okay, this is just like the generalized molecular formula. Make sure you use the one out of your data booklet. Okay, it's on page 8. Okay, when you're writing it. So Ka is equal to, it's going to be our product, so H3O plus times our conjugate base. So again, it's on page 8. So C3H5O COOH2 COO minus. Okay, so this is the one we get out of our data booklet. Okay, divided by, or actually that's the conjugate base out of our data booklet, and then divided by the concentration of C3H5O COOH3. Okay, and so that's, again, it only takes one H, and so that's why you kind of write it this way each time. And then it's equal to, okay, we're given the Ka for this, so 7.4 times 10 to the minus 4. So just writing the expression, we're including the Ka because we have it, it's in our data booklet. Okay, we'll do question 2 also. So a chemist prepares a 0.1 mole per liter solution, okay, of baryteric acid. Okay, the chemist measures the pH of the solution, records the value of 2.5. What is the acid ionization constant, and what's the percentage of molecules were ionized? Okay, so again, to start with, okay, we need to write out its ionization formula. For this one, it's hard to know what it looks like with the C's and the H's and stuff. So we're just going to write it. Actually, we only have one H, so this has to be our H for our acid. Okay, so we have HC4, or never mind, sorry, we got 3 H's there. N2O3. That's our acid plus water. That's going to produce hydronium plus our base. So we're just going to take one of the H's. We're actually going to take one of these H's out, but for this, I wouldn't be picky because there's no way to it's hard to know where to take it from. N2O3, and then since we took out H away, it's going to have a minus charge. And these are aqueous. Okay, we're trying to find the Ka, so we need an ice table for this one. So we'll get that prepared. Okay, so now we'll fill in the values that we know. So we know that this is 0.10 moles per liter. We know that these are both 0. These are both going to be plus X, so both of these values will be X. Okay, and then this would be minus X, so this is 0.10 minus X. Okay, that gives us our table. Now we try and, for any of these, we have to solve for X. What is X? So we look up here, our value that's going to help us, okay, is 2.5. So again, a pH of 2.5. From that, we can get our hydronium concentration is equal to 10 to the negative pH, so 10 to the negative 2.5. So our hydronium concentration is equal to 0.00316, okay, which is equal to X. So now we know this number and we know this number. Okay, for our acid ionization constant, we also need to know this number, so we just go 0.10 minus X, so minus this number here, and we get this is equal to 0.0968. Now we put those numbers into our Ka formula. So our Ka formula, we have our conjugate base. I'm just going to put, I'm just going to use the generalized term here just to kind of make it a little bit quicker, times our hydronium times our weak acid. Okay, so we put our numbers in now that we know them. Okay, so these are both the 0.00316. Again, because they're both the same, I'll just square it and then divide by 0.0968. So our Ka is equal to 1.0 times 10 to the minus 4. Okay. And then for our percent ionization, okay, we just have our it's our hydronium value, so 0.00316 divided by, we always want to use our initial HA value, our initial weak acid. These are both moles per liter, times 100%, and we got our percentage is equal to 3.2%. Okay, so there's one of our answers. Here's our other answer. Okay, and that's that question. Okay, questions 3 and 4 are similar to question 2, so you can use that as a reference. Okay, again, if you want to see how it's done, just let me know. You also have the answer keys. Okay, just be careful. There are some errors on my answer keys, so if you think you found an error, just let me know and I'll fix it. And I also can kind of tell if you're just copying using the answer key, because like then you make those same errors that I've usually fixed. Okay, so for this one, we're looking at hydrofluoric acid. Okay, write the Ka expression. I'm sure you guys can do that now. Okay, I'll do this part B. Calculate the hydronium and fluoride ion amount concentrations, the pH, and the percent reaction if we have 2 moles per liter HF at 25 degrees Celsius. Okay, so to start, we write out our balanced ionization equation. Then we fill in our ice table. So I'll start with that. Okay, so there's our ionization equation and our ice table. Now we want to fill it in. So we got to start here at 2.0 moles per liter. Okay, it's going to change by minus x, so we got 2.0 minus x. Okay, and then another thing, like we can find the Ka for this in our book. So our Ka is 6.3 times 10 to the minus 4. Okay, these are start at 0. They're going to be plus x, so these will both just be x. Okay, whenever you get these numbers here, you always want to do a quick rule of 1000 check. So 2 divided by 6.3 times 10 to the minus 4. This number is greater than 1000 when I put in my calculator. So really what I can do is just forget about this here, the minus x. This is just going to be 2.0. Okay, so now we need to solve for x because we want to know the pH. In order to know the pH, we need to know this hydronium concentration. So we put it into our Ka equation. So our Ka equation, which we write down up here. Okay, so I should show it, but since we already showed it up here for you guys, I'm not going to worry about it. So 6.3 times 10 to the minus 4 is equal to x squared over 2. Okay, so times both sides by 2. That cancels with that. So we got x is equal to the square root 6.3 times 10 to the minus 4 times 2. So x is equal to 0.03546. Or 354.96. Okay, now we know what X is. Okay, again, pH is equal to negative log of our hydronium concentration. So pH is equal to negative log of our X value, so 0.035496. So we get our pH is equal to 1.45. Again, 2 digits means 2 decimal places for that. Okay, now we also want percent ionization, so we have our concentration of hydronium over our concentration of our acid initially, and we get 1.8%. Okay, so that's where we're solving for that one. Okay, again, like I said before, if you ever aren't sure, put a nice table down, kind of see where you get. Okay, always like when you get like something minus something, do a quick check rule of 1000 because that'll make it a lot easier when you're putting it into this equation here. Okay, the next couple of questions are similar to the one we just did, so I'm going to move on to question 9, and I'll do questions 9 and 10, and then hopefully you can get the rest. So for question 9, hexanoic acid, commonly known as caproic acid, so C5H11COOH, occurs naturally in coconut and palm oils. Weak monoprotic acid, Ka is 1.3 times 10 to the minus 5. A certain aqueous solution of hexanoic acid has a pH of 2.94. How much acid in grams was dissolved to make this solution? Okay, and so this one, it's going to be using a bit of stoich, okay, but we first need to kind of find out what is our concentration. Once we find our concentration of our acid, then we can find out how much, what the mass would be in grams. Okay, so again, like pretty much every question in this unit, we start with our balanced, in this case, ionization equation, and then we put our ice table down. So we'll start there. All right, so what we're actually looking for is this concentration here. So that is kind of our unknown. So we know that these both start at 0. These are both plus x. So these are going to both be equal to x. Okay, this water doesn't matter. Okay, this would be minus x. Okay, and so like whatever our concentration is initially, so concentration minus x will equal our concentration at equilibrium. So this value here, we'll just say C minus x. It's kind of giving us that. Okay, so to solve for this, okay, we want to find out like any numbers we have. So we have a pH. Oh, we have a Ka 1.3 times 10 to the negative 5. Okay, and then our pH is equal to 2.94. So from our pH, we can solve for this x value here. It's 10 to the negative pH will give us this value. So 10 to the negative 2.94. So our hydronium concentration is equal to 1.1 times 10 to the minus 3 moles per liter. So that's our concentration of hydronium just by using our pH, which means that's also this concentration. So both of these we're given, or we have that concentration. And then now we want to solve for initial concentration, or well, we want to solve for this concentration. One thing to note is if our, so I guess we'll solve for that. Right now we're gonna do a rule of 1000 check. So our initial concentration, or what is it here? Sorry, one thing. Okay, so right now we're just going to solve for that. Like we won't worry about the C minus X. We're just going to worry about like we'll say what is this number here. So we'll use N as our variable. And then we can see if we have to go like minus X earlier. Okay, so this is our equilibrium, our acid ionization constant formula. Okay, put our numbers in. So we got 1.3 times 10 to the minus 5 is equal to 1.1 times 10 to the minus 3 squared over n. Okay, so basically these two will switch spots here. So n will equal 1.1 times 10 to the minus 3 squared over 1.3 times 10 to the minus 5. So n value is equal to 0.1014. Okay, now we kind of know this. This is this value here. To find out if it's the same up here, we can do our rule of 1,000. So rule of 1,000, so we'll take this number, and this is in moles per liter, so 0.1014 divided by our Ka, and this number is greater than 1,000. So basically our initial concentration will equal this. Okay, now we know that. Okay, now we're going to use stoich to kind of solve for this. So we know our concentration of this is equal to 0.1014. We can find our molar mass. Molar mass for this is equal to 116 116.18 grams per mole. And then we also know our volume is 0.1 liters. Okay, so now we're just we're using C equals N over V and then mass times molar mass, or just use stoich. We don't have to actually use a bunch like stoich because we aren't going to be multiplying by any of these ratios. We just have to use we'll use C is equal to N over V. So if we want to solve for N is equal to C times V, and then mass is equal to moles times molar mass. Okay, I'm going to do it in one. So we're just going to take this number. We have the number. This is, I shouldn't write this as N. This is my concentration. I'm going to times that by my volume. So 0.100 liters. Now I'm going to times that by my molar mass. Okay, 116.18 grams per mole. Okay, so my moles cancel, my liters cancel, and then I'm left with grams. And I got 1.2 grams. And that is my final answer. That's how many grams I'd need to make that solution. Okay, last example here. So question 10, hypochlorous acid is used to make bleach. A chemist finds that 0.027% of hypochlorous acid are ionized in a 0.4 mole per liter solution. What is the value of Ka for this? Okay, so again, we want to write down our acid ionization formula. So we have hypochlorous acid plus water will produce hydronium and our conjugate base. We know that 0.027% goes forward. We're looking for our Ka. So our Ka will be equal to our concentrations of hydronium times our concentration of our conjugate base divided by our concentration of our acid. Sorry, I forgot to write down our ice table. So we have our ice table. This is our Ka expression. Okay. Now we need to solve for one of these values. So we can find, using the percentage, we can find the concentration for X. So again, percent ionization is equal to the concentration of hydronium divided by our initial concentration of our acid times 100%. So now we just need to rearrange this. We have this value, we have this value, so we're going to solve it for hydronium. So if we're looking for hydronium, it's going to be our percentage divided by 1,000 times our concentration of our acid. Okay, so we can put our numbers in now. So 0.027 divided by 100 times 0.40 moles per liter. And our concentration of hydronium is equal to 1.08 times 10 to the minus 4. Okay, so this is equal to X. Okay, and then we need to know, so like both of these concentrations are, there's 1.08 times 10 to the minus 4. 0.08 times 10 to the minus 4. And then this one, we just go 0.4 minus that value. Okay, and that value ends up being so small that, again, like it's not significant. So this ends up being 0.40, the same as it was. Okay, so now we put our numbers into our Ka formula. So we got 1.08 times 10 to the minus 4 squared divided by 0.40. And our Ka is equal to 2.9 times 10 to the negative 8. And that is our answer.